Morning, everyone. So yesterday we recapped sort of some of the major concepts from the mole chapter. We saw that 1 mole is an Avogadro number, 6.02 times 10 to the 23. We started doing that mind map where we can actually see the mole in the middle of the diagram. Once we go through mole, we can go to mass using molar mass in the periodic table. If we were a gas at SCP, we can use molar volume, the 22.7 liters, or if we're a solution, we can actually use concentration. I'm going to give you a quick practice question for those conversions. We also ended off with a little bit of practice with reactions, so I'm going to give you one style of that as well. Once we go over these ones here, we're into practicing a little bit of stoichiometry. So, just as a quick warm-up here, I want you to find for me, I want you to calculate the mass of 24 liters of ammonia gas at SDP. I'm going to do a percent composition one, sort of related to the empirical, but hopefully a little bit easier. So I want you to find for me or find the percent water in cobalt chloride. Let's do tetrahydrate. And then 3, I want you to predict, balance, classify. So this is sort of doing the reactions here, and this one I want you to do, let's do KNO3, and let's react it with let's do KI and PbNO3 too. Alright? So, again, I would encourage you just to pause the video, try it out for yourself, and we'll see how we do. Alright, assuming that you've done that here, let's calculate here. Well, what's ammonia? Ammonia is another one of those common names I want you to memorize, right? Just like you memorize water to be H2O or methane to be CH4. Ammonia is actually NH3. Careful, it's different from ammonium as a polyatomic. So far we know ammonia, it's a gas at our standard conditions here. When we're at our standard conditions, I know 1 mole is equivalent to 22.7 liters. So either you work from the diagram or you just have internalized that here. We want to find question mark as a mass. If you're ever stuck, just start off with the number given. So currently here it's 24 liters. I want to get rid of liters and go to moles, so I can use the 22.7 liters for a mole. I needed 22 for every box. I have a little bit over 22, so I have a little over a mole. And in this case here, I want to get to mass. So good, if I have moles, I can just go to your periodic table, find the molar mass. The nitrogen weighs 14, hydrogen weighs 1. So we're going to get 17 grams there. Numbers on top you multiply, on the bottom you divide. 24 times 17 divided by 22.7. This gives me here 18 grams. So using that mole diagram, we can sort of navigate around. The second one here, so we have a hydrate. Make sure you can name that. So this one here is cobalt. Cobalt is a transition metal, so I would expect it to have more than one charge. So maybe I have cobalt 6 chloride here. Somewhat bigger of a compound there. How do you name this hydrate part here? Because you have actually 4 waters. We're going to use a prefix for 4 here, tetra. Remember, the ending is just going to be hydrate. We are hydrated by 4 waters. You might find, oh, I don't have this cobalt with this charge here. They just gave you the most common charges. It's possible that the compounds may actually use even more charges than listed. But for that compound here, what we're going to do essentially, to find the percentage water, what they want to do is they want you to tell me how much mass is water inside the mass of the entire hydrate. So in this case, what I'd do is I'd say, well, I have 4 waters, so I'm going to go 4. The water is going to weigh a mass of 18. I just need the molar mass of the entire compound. So cobalt is 58.9 plus 6 times 35.5. I need to add the 4 times 18. In total, this is 343.9. So this is the entire hydrate. The 4 waters in this compound here leaves me with a percentage, 4 times 18 divided by this one. I'm getting a decimal 0.209, or in percentage, this means 20.9%. We did a lab in Chem 11. Basically, if I knew the percentage of water, it's a basic sort of empirical formula style question just to get back to, oh, I would need to have a 1:4 ratio to represent 20% by mass is actually water. All right, so this third question here. So we have our predicting, balancing, classifying. It's a sort of a reaction here. We know it's a double placement reaction, so we know they're going to swap partners. So I'm going to swap, let's say, the PB with the K. So it's going to be PB and I, and then we're going to have K with NO3. As I mentioned before, in general, these numbers here don't drag over. The NO3, that 3 would, because the nitrate is a grouping together. But remember, this 2 here is based on what compound that we're currently in. So even though the double replacement sort of helps predict for us what the combinations are going to be on this on the right-hand side, we still want to check the charges ourselves. So for example, K is an alkali metal, +1. Nitrate is a NO3 with a -1 charge. You can find that on the polyatomic. Once you work, 1 to 1, it cancels out here. So it's good to just, those charges are still there, but remember we worked out the ratio so that they cancel out. The lead is a little more tricky. Lead can actually be +2 or +4. Because we're totally predicting here, you could do it with lead 2 iodide, lead 4 iodide. In this case here, it's actually a little bit easier. I asked myself, what charge is lead using here? It's not impossible for lead to change charge, but if I already know the charge on this side, let's just keep the charge the same. So in a similar fashion here, nitrate is a -1. I needed 2 of them, so that's -2. Lead is currently using as +2. Let's guess at it where lead is using as +2. Iodide is a halogen, so iodide is -1, so I would also need PbI2. Once you work with those ratios, again, it's important for you to just basically hide those charges there. In the lattice, we've gotten rid of those charges. Make sure the overall equation is balanced. So I have 1 Pb, 1 Pb. The nitrates I can balance as a group, so I have 2 nitrate groupings. I only have 1 nitrate grouping, so let's put a 2 there. That screws up the K's, so I put a 2 here. 2 K's and 2 I's perfectly matches up. If you're finding, I'm changing this number and that changes this one, this changes this one, and you're going back and forth, chances are you've written one of the formulas incorrectly. So that is a balanced equation. You'll still balance it in the fashion that we did. Usually they like framing it in terms of what are the sum of the coefficients. So now that you have all the numbers you need in the recipe, I want you to just add up certain numbers. I want to say, what are the sum of all the coefficients? So you would add up to, don't forget these ones here are 1s, even though it's sort of implied here. 2 + 1 + 1 + 2. The sum of all of them is 6. What are the sum of the coefficients on the reactant side? 2 + 1 is 3. The sum on the product side is also 3. You still balance it in the same fashion, but especially for multiple choice, you add up the ones that they asked for. In this case here, because this one is a double replacement reaction, we can do it in a little more detail. This is called the formula equation because I've written all the formulas for you. Double replacement always makes it look like I start off with 2 things. Because they switch partners, I end up creating 2 new things. I want to investigate whether that's true or not by doing the complete ionic equation and by doing the net ionic equation. Towards the end of our review yesterday, we started saying, well, we want to check the solubility chart. We want to check to see who's soluble and who's not soluble. So K is an alkali salt. Alkalis are soluble with everything, so I'm not going to even bother checking that one there. Nitrates as well. Nitrate salts here you can find on that solubility chart. Nitrates as a negative ion with any positives are actually always soluble. Soluble means it dissolves, so it's going to be AQ. So I'm going to have AQ. Again, for a properly worded question, you should find the first 2 are aqueous. Basically, I pre-dissolve the first mixture, I pre-dissolve the second mixture, just to get the ions swimming around, just to get them able to collide a little easier. If they were solids, it's not impossible to react. I've done a reaction where you can actually squeeze and mix powder together. It's just that in the solid state, there's not a lot of energy. The particles are just vibrating. It's not as easy for things to contact. You basically pour them into one container all together. So now all 4 ions are together. We check it. K is perfectly fine, dissolved with the nitrate aqueous. But when you check the chart here, iodide, that combination with lead, is actually a low soluble mix. So because it's low soluble, again, we end up with a solid. First thing, we started with a clear bottle of Ki, a clear bottle of PbNO3. Those are fully dissolved. Suddenly, we get something that's solid. Suddenly, we get a solid that crashes out of solution. That's what we're going to call a precipitate. So for a complete ionic equation, I'll remind you, you're going to separate, you're going to dissociate any aqueous guys, and then you're going to leave any solids and, in a later case, liquids alone. So we had 2 Ki because it's aqueous. Even though the bottle is labeled 2 Ki, I can actually write that 2K plus and 2 iodide minus. I still carry around the numbers because I want to stay balanced here. I have PbNO3 too, also aqueous. It means the Pb is not holding hands with the nitrate. It means Pb is by itself. The 2 nitrates, although water is good enough to separate positive or negative, water can't destroy the covalent compounds in the polyatomic. So let's leave the polyatomic alone. The PbI2 here is a solid, so I'm going to leave that. When those 2 find each other, they actually physically bond together and they stick together. So PbI2 is a solid, and then we end up with KNNO3. Again, 2K plus and 2NO3 minus. Even though I've labeled it as KNO3, because we are also aqueous, it means that they're actually not bonded. What we want to do here, we want to cancel out any spectators if we have them. That's switching us from a complete ionic to what's referred to as a net ionic equation. For the net ionic equation here, we're going to cancel out any spectators, like spectators at a hockey game. They just watch the game, they don't participate, they're the same before and after. Well, I had 2k plus before, I still have 2k plus afterwards. That would be a spectator. I have 2NO3 before, 2NO3 afterwards. That's also a spectator. They were swimming around beforehand. Sure, they happen to be swimming around all together now, but they are exactly the same before and after. So overall, the reaction is actually the iodide from the first bottle has found the lead from the second bottle, and effectively, if you sort of dig through the details, this is actually the overall equation. This is all that's happening. We actually only end up making one compound, and that explains the precipitate. It's totally possible that you can end up with two solids or both aqueous. In the both aqueous case here, even though double replacement makes it look like we switched and changed partners here, if everything is aqueous, it means everything is fully swimming apart. And if they're swimming apart, we haven't actually made any new compound. So again, just for double replacement, we can do that detail there. Okay, so there's one other thing we can recap before we actually jump into stoichiometry. Basically, for those 6 types of reactions that we did, not only do the chemicals potentially switch partners and react, sometimes the reactions end up releasing energy or they end up absorbing energy. I just want to rehash with you those 2 terms. We can have what's referred to as an endothermic reaction. For an endothermic reaction, heat actually enters the system. How do we tell something to be endo? We're going to look for the heat term on the left-hand side. This will become important for us in our first chapter in Chem 12. If the heat term is on the left-hand side, at first you're going to be like, oh, the left-hand side is hotter. But again, you're going to need to focus here. The chemical A is actually grabbing heat that wasn't his. When A ended up becoming B, I don't see the heat term anymore. That means the heat has been absorbed into A. To plot that out here, we can do what's called an enthalpy level diagram or energy level diagram. And basically what we're doing here is we're plotting the relative amount of heat inside these particles here. So we're going to plot enthalpy with H. We're going to plot it either against time or plot it against just a reaction axis. And basically what's end up happening here, I'm just going to give you that name. This is enthalpy. It's the energy in the system. So just the part that we're studying, just the reaction. So A started off at some amount of energy. It's actually some limitation of ours here. We actually don't know how much energy A starts off at. Maybe I should do A here and question mark. But fortunately for us here, we just care the change. A is going to steal a bunch of heat that's not his. So imagine putting a lot of heat inside A. Its energy is going to end up rising, and we're going to end up getting to B. Again, I don't know exactly what the energy that B has, but what I do know is we are higher than what we were to start off. Because we're using H for the symbol for enthalpy here, I can just sketch the reactant arrow over. I'm going to draw the arrow upwards. This is now a delta H. The delta H, the change in enthalpy, is going to be positive. I end up with more energy afterwards than before, and therefore it's endothermic, it's absorbed energy. In fact, the first thing that we're going to do in Chem 12, we're going to say, yeah, A started out low, B started out high. It doesn't just connect the dots here. It actually is, there's actually an energy barrier in between. We'll talk about that energy barrier as actually controlling the rate itself. It actually controls how fast the reaction occurs, and that's going to be a new concept that we're going to do. So that's endo. That's great. That's on the left-hand side here. We're going to do exo. For an exothermic reaction, essentially heat exits. Heat ends up leaving. So to show you heat's leaving, we're going to have, let's say, C becomes D, and it spits off energy. They can just use terms like plus energy, plus heat. They may even give you a number. Let's say it's plus 10 kilojoules per mole. All we really care is which side it's on. If it's on the left-hand side, endo. If it's on the right-hand side, exo. Sometimes they try to confuse you and they try to go like C minus 10. In this equation here, it shouldn't actually be negative. If we really wanted a minus, I just make it a plus on the other side. So it should always be a plus. Left side endo, right side exo. Let's see if we can draw an enthalpy level diagram again. We're going to label it with H. We're going to plot it against the reaction coordinate. A reaction coordinate essentially means we have reactants as ingredients, we have products as the remainder, and basically going to left to right, we end up going forwards. So that's the forwards reaction. We can think about going in the reverse direction. So this is the forward reaction. The reverse direction, taking products and going backwards. Most of the reactions that we talk about are reversible. But at least for the forward reaction, we started out with C having some energy. As C becomes D, it ends up releasing off energy. That energy escapes to the surroundings, so therefore D actually ends up at a lower energy than where it started. If I do that same work with delta H, I sketch the reactant arrow over. This arrow actually points downwards. The delta H is actually negative. So there's two ways to tell endo. If the heat term's on the left-hand side, and the heat term and the delta H term is positive, there's two ways to tell exo. If the energy or the heat term is on the product side, or if the delta H is negative. Right? They would have to give you this information to actually tell you whether overall energy is input or overall energy is given off. Likewise, though, in our first chapter, we're going to find that there's an energy hill, there is an energy barrier, but you see that this energy barrier is not as big as the energy barrier before, so you would imagine exothermic reactions should be more likely to occur, should be more spontaneous. Especially, even though this is looking at the system here, usually for us, we are the surroundings. So if you imagine, let's say, there's a test tube where this reaction is actually occurring, and suddenly all this heat is actually entering the test tube, where all that heat is actually coming from, if I just hold the test tube from the outside, all that energy is being stolen away from me, I would actually end up feeling colder. Surroundings get colder. Or in contrast here, if this reaction was happening in the test tube and the reaction was giving off a lot of heat and I was just holding it from the outside, I'm always too macroscopic, I'm always too large. So what's going to end up happening is, even though they might just say temperature gets hotter or energy is released here, we are always surroundings. We are never microscopic enough to actually figure out what the particles themselves are doing. I just figure they do the opposite. If my hands get hot, it's because the energy in the system actually went down. Okay? So keep an eye out for that there. We did do a few practice questions, especially if we have the number. We can do a little bit of stoichiometry with that. Just let me give you a quick taste of that one there. So let's say calculate the heat released in burning 5 grams of magnesium, given the delta H is negative 1200 kilojoules per mole. Right. We're not going to do this style of reaction too much, but just for completeness sake, I wanted to show it to you. We're going to start off with the equation. So what does burning of magnesium look like? So that's Mg. We know the chemical we need for burning is an oxygen. We would normally fully get our products CO2 and water, but in this case here, we don't have a carbon or hydrogen source. In this case here, we're just going to end up with just MgO. So it's like a synthesis reaction here. I definitely want to balance that there. So it's a 2, 1, and a 2 there. This time it's starting us into the stoichiometry aspect of it. This time I have 5 grams of magnesium, and I'm not interested in just calculating the amounts of oxygen and magnesium oxide. We'll do this part right after. I'm interested in actually calculating over to the heat term. The heat term is actually negative. That negative means exo. That means the heat term is on the right-hand side. And they actually give you this value. This is the reaction that ended up giving off a really, really intense bright light. That actually gives off plus 1200 kilojoules. When it says per mole, sometimes they even jot that per mole. That per mole actually stands for per mole of reaction. Basically what that means is every time you run the statement once, 1200. You do the statement again, 1200. You do the statement again, 1200. Every time you do the mole, it's 1200. So all we're going to have to do here, we're going to calculate the amount of energy or the heat that's released. We're going to start off with 5 grams. Because I'm interested in comparing sort of molar amounts here, I need to go through mole ratio. So I'm going to use molar mass here. 24.3 is 1 gram, 24.3 grams for a mole. And then what I'm going to say is, wait a second. Every time you run this statement, you actually need 2 parts magnesium. For every 2 moles of magnesium, that's like running the statement once. And then we're going to factor in, well, for every running the statement once, Rxn is reaction. I end up getting 1200 kilojoules. What about the negative? Well, negative just means it's going to be leaving. So when I calculate the number, this is how much energy is lost. So 5 gram piece of magnesium ribbon, divide 24.3, divide 2 times 1200. This gives me, give or take, 120 or so kilojoules. And that negative there just can be written in words. 1200 is released for burning. So sure, you would, if you burn out a mole of reaction, you get 1200, but this 5 gram here is nowhere near a mole. I would need 24 grams for a mole. But for this amount that's released, every time you run that statement, especially because that mole ratio is sort of against you here, it's only going to release 120. In fact, for this part here, we can just shortcut it. We can say, yeah, I know, we're just running 1 mole, just going through 1 time. I can say, running at one time is for every 2 moles of magnesium, and you can do the 1200 kilojoules right away, and that's just a nice simplification for that latter part there. Again, we won't need that part for too much, but that's a nice little segue into doing stoichiometry. Remember, stoichiometry, we basically put everything back together, all those molar conversions, molar volume, molar mass, concentration, and we try to do a prediction between, if I know how much starting amount, how much ending amount would I have? So let me just recap here, stoichiometry. We had summarized this on a mind map, so essentially what we started doing is we started having, well, we have moles of one chemical, I'm going to call it A. We want to get to moles of another chemical. The only link in between these two here was something called a mole bridge or a mole ratio, and this had to come from your balanced equation, which is why we rehashed a little bit with equations, predicting, make sure the recipe is proportioned correctly before you follow that. That works whenever we're comparing numbers. So it's going to work comparing, let's say, a number of molecules to a number of molecules. It's the same mole ratio. It's the same recipe. It will not work for masses, however. So while from numbers we can use, let's say, 1 mole is Avogadro's number, it will not work for masses because different ingredients weigh different amounts. So we might need to use the molar mass from the periodic table, PT for short. We might be interested in getting back to mass. So we'll have to convert it to a number first, and then we can jump over. We had 2 volume bubbles. One of the volume bubbles here was for a gas at STP. For this one, we could use molar volume. 1 mole was equivalent to 22.7. Didn't matter what type of gas we were. If we were concentration, almost getting into like a titration aspect here. For volume, this is specifically of a solution. We would end up using the concentration. Pretty much the big idea here was get yourself back to mole first, and then I can use a mole ratio. If later on you want to convert it afterwards, once you jump chemical, you're more than welcome to use the 22.7 again and use the new concentration again. Right? So this is the diagram that I just want you to internalize. I know it's been a while, maybe you've forgotten some of this, but let's just practice through a few types of conversions here, and then we're going to add in that limiting assess little bit of detail. So let me start off giving you an equation. I'm going to give you NH3 reacts with O2. This ends up forming water and NO. Right, so slightly harder to predict, so they actually hint at what it is. I'm going to ask you first to balance it. What are the coefficients that you need to make sure this recipe is balanced? And then I'm going to ask you to try a little bit of stoichiometry. So first question, just balance the equation. Make sure your ratios are balanced. Sometimes we refer to this equation currently as a skeletal equation. A skeletal equation is like the skeletons of the equation. It's an unbalanced equation. Once you have that balance, I want you to find for me when 15 grams of ammonia react. So that's the sort of starting condition. I want you to see if you can find for me what mass of oxygen reacts. So that's also a reactant, so that's how I can say reacts here. And then I can also ask you here what volume of nitrogen monoxide. Right, that one there has a prefix, so you can imagine that's a covalent compound, so that's the NO afterwards. Produces or forms. Right. So again, I would encourage you to just pause the video, try it out for yourself. All right, in terms of balancing first, so we're going to have NH3, so 1N, I have 3 H's. The 3 and the 2 are not going to balance, so at first you might put a 2. Later on you're going to realize even that isn't enough, so this one eventually actually needs to be a 4. So 4N with a 4N here. 4 times 3 makes 12, so that means I need 6 times 2. 6 O's and 4 O's means I have 10 oxygens, I have 5. That's the simplest whole number ratio that we have. So far what we're saying is for every 4 molecules of ammonia, 5 molecules oxygen, 6 molecules water, 4 molecules NO get produced. It could be 40 molecules. Well, for every 4, it takes 5. So 40 molecules would take 50 molecules, 60 and 40. We can take 4 moles. 4 boxes of ammonia, 4 boxes and 5 boxes make 6 boxes, 4 boxes. Whenever we're comparing numbers, that mole ratio works. And now the setup here is in part B, I'm going to decide to react 15 grams of ammonia. What I try to do is I do a roadmap for myself here. I'm interested in getting to mass of oxygen. So I'm interested in getting to grams of one thing, grams of the other. I cannot use this 4 to 5 ratio because ammonia and oxygen weigh a different amount. So first thing you have to do is find moles, use the mole ratio 4 to 5, and then go back to grams there. Just while I have it on the board here, I also want to take the 15 grams here, and I want to get to volume of nitrogen monoxide. Nitrogen monoxide being a covalent compound, I can imagine it's a gas. I can assume it's a STP. Again, I'm trying to compare what I know about one chemical to another. The only link is a mole ratio. Once I get to moles, I'm going to use the mole ratio over, and I can use 22.7 to get back to liters there. So let's see if we can lay out our work here. It's best if you can do this all in one row here. So how many grams of oxygen starting from 15 grams of ammonia? I have predicted this is going to be a 3-step conversion. First one, grams to moles. So cancel out grams goes to moles. Second step, moles of ammonia jump from ammonia over to oxygen. Moles of ammonia to moles of oxygen. That's through the mole bridge. Once you've jumped over to oxygen, we're pretty much home free. For every 1 mole of oxygen, how many grams there are? So 3-step conversion, make sure top unit cancels bottom unit in all of this. Let's go our way through here. The molar mass for ammonia, 14 for N, 1 for each of the hydrogens, so we have 17. Make sure your molar masses have 1 decimal place. I don't want to accidentally lose significant figures. 17 grams for a mole. The mole ratio says when there's a 4 in front of ammonia, there should be a 5 in front of oxygen. 4 in front of ammonia, 5 in front of oxygen. And then careful for oxygen, even though O on the periodic table is given as 16, because this one here is actually a diatomic oxygen, we actually want to put 32 grams per mole. Sometimes people accidentally confuse, well, what about this 5 here? Wouldn't I go 5 times 32? I've already dealt with the 5 here. If I accidentally doubled the 5 again, I would have double counted that 5. So long story short here is once you have the balance coefficients, just to make sure you only count it once, these coefficients only enter the mole ratio step. That way it keeps your molar mass the same. Even as you do molar volume, 1 mole is 22.7, all that's the same. So the coefficients only go into that mole ratio step. Numbers on top you multiply. Don't bother typing in any times ones. 15 times 5 times 32. On the bottom you divide. Divide 17, divide 4. Make sure you type this in your calculator yourself so that you end up getting good practice at this. 35.3 grams of oxygen. Let's do the second one here. What volume nitrogen monoxide gets produced? So volume is going to be liters. We want to know NO. It's possible I could have taken this 35.3 and went from there, but just in case I got that wrong, let's just start off back with the 15 grams from earlier. So 15 grams of ammonia, this one divides 17 grams per mole. This time I'm going to jump from ammonia over to NO. Even though it is a 1-to-1 ratio, well, we'll just still write 4 and 4. So if I make a mistake, I can double check where did I get those numbers. And now because we're a gas, you can assume STP, 22.7 liters for a mole. So here we go, 15 times 22.7 divided by 17. I'm not even going to type in the times 4 divided by 4, that just cancels out. And this ends up giving you 20.02, so 20.0 liters. So stoichiometry actually gave us quite a lot of power in actually trying to figure out how much actually needed is to react, as well as how much forms. What we're going to do in the next question here is we're going to throw in that little complexity here with limiting excess, and we'll see how we do. So let's just see how this question is going to be worded out here. So standard stoichiometry problem here. When, let's make it 20 grams of oxalic acid are reacted with 600 milliliters of 0.900 molar lithium hydroxide according to, so they're going to give you this equation here. Oxalic acid here, we notice that there's no hydro part, so it's based off the polyatomic. We're looking for oxalate. Oxalic acid is actually H2C2O4. We're reacting this acid here with lithium hydroxide, LiOH. This one here is acid-base neutralization here. Basically, the lithium is going to swap places with the hydrogen there, so we're going to get Li with oxalate. Even if oxalate were not on the data booklet here, you can just say, well, for this compound as they've given me, there's actually 2 H's that are needed to counterbalance the C2O4. This actually tells you your C2O4 actually has a -2 charge. Lithium as an alkali only has a +1 charge, so I would need Li2C2O4, and then we end up getting water. So usually they just give you this equation here. They want to test the limiting excess in this question. So H2C2O4, we need 2 lithium hydroxides. I'm integrating 2 waters. There's actually a nice little hint here for a neutralization. Effectively, I know it's the H plus from the acid that reacts with OH minus. These actually react in a 1-to-1 ratio to end up forming your water. So far, the oxalic acid at the very least is going to have 2. Well, of course, I would need 2 hydroxides, and that would end up giving you 2 waters. That's where I actually get this number 2 and that 2 from. But there we have our equation. This question here, I want to know which is limiting, which is the chemical that runs out first. Remember, when the limiting runs out, it stops production. If I have a ton of the other ingredient left over, it doesn't really matter which is limiting. B, I want you to find or determine the moles of the salts produced. And then part C, how much excess remains. So as we sort of look our way through this problem here, how do we know this is a limiting excess question without them saying it, right? Well, in this problem here, we're given, let me just sort of list the values here. I have 20 grams of oxalic acid. Oxalic acid is H2C2O4. They gave me 20 grams. That's how much I bought of the first chemical. It's reacted, they actually give you 2 numbers here. We have 600 milliliters, 0.9 molar, but that's talking about lithium hydroxide. So we have 600 milliliters, and we have the concentration as 0.900 molar. Whenever they deal with concentrations, they have to give you 2 numbers to do the conversions. But I would know that this is a limiting excess question because I went to the store, I bought this much of the first ingredient and this much of the next ingredient. Because I totally randomly made up these numbers here, chances are one of these chemicals runs out. When one of these chemicals runs out, it totally stops the reaction. Although you could totally do a comparison between, well, if I have 20 grams, how much volume of LiOH would I need? You can do a comparison between these two here. What I usually show people is I try to do part A and B together. So even if on the test it says part A leaves you a big blank room and then part B, you can still do this work once and you can answer both parts together. And if you remember, our strategy is, because there's a good chance that both of these could run out first, let's do those assumptions. Let's pretend the 20 grams runs out. If they don't give me any information, you're more than welcome to calculate over to the salt, to the H2O, whichever you want, because they specifically say the salt, in this case here is the Li2C2O4, and they want moles, we may as well go to this chemical and go to the unit that they want. So what I'm saying here is you're going to have the 20 grams. If all of it reacts and ends up producing, how many moles of lithium oxalate would I form? As a second step, we're going to calculate over. If we use the lithium hydroxide amount that I bought here, let's go to the same unit of the same chemical. Whichever one is a smaller number is going to be the one that was limiting. So we're taking turns assuming. So how many moles of lithium Li2C2O4 get produced? Let's start off with 20 grams. And I'm going to emphasize this is oxalic acid, H2C2O4. I'm going to do that conversion over. And in a similar fashion, I'm going to go to the same unit, question mark moles, of the same chemical so that I can make a comparison. And this time I'm given 2 numbers. This time I'm given volume and concentration. I always see volume is a little bit easier to work with because the concentration molar is actually a moles per liter. That actually has a fractional unit that actually becomes a conversion. Because we know it actually is going to be liters coming up, I'm going to still convert that into liters though. So 0.6 liters of LiOH. So I'm going to do 2 separate conversions here, do our stoichiometry practice. We want to get from mass of the oxalic acid over to the lithium oxalate. So what we're going to do is we want to find grams per mole, and then I can use the mole ratio. My mole ratio says for every 1 part oxalic acid, it's just 1 part of your salt. For every 1 mole of H2C2O4, it is 1 mole of Li2C2O4 as well. So 1 and 1. So let's do the molar mass here. So every hydrogen is 1 times 2. Plus 2 times 12 for the carbon, plus 4 times 16. Oxalic acid calculator just gives you 90. I still put on 90.0 because I want to have more significant figures if I can. And therefore, I just go with the 20 grams oxalic acid. I should be able to make here, give or take, 0.222 moles. Right? I don't know if that much forms because this was an assumption. Let's do the same for the other calculation here. Because I have a volume of LiOH, I'm going to use concentration to go liters to moles. It's always tempting to use 22.7 because that's an easy conversion. But remember, 22.7 only works if we're dealing with gases. This time here, because we're not, I'm going to use the concentration instead. This one says for every 1 liter, there should be 0.900 moles for it. For every 1 liter, 0.900 moles for it. My mole ratio here says for every 2 parts LiOH, and then you get 1 part Li2C2O4. You crunch your numbers through. There's no guarantee of anything here. These numbers here could be totally wildly different, just depending on how much I decide to purchase at the beginning. I could have purchased so much more of the oxalic acid as LiOH or vice versa. And now looking at these two numbers, although going into it, I didn't know which was limiting excess, I now can see I only had enough oxalic acid to produce 0.222, while I have enough points of the 600 milliliters of the lithium hydroxide to actually produce 0.270. It's always the lesser number that gets formed. By the time I create 0.222, this chemical cuts out. Without the oxalic acid, there's nothing else for the lithium hydroxide to actually react. So, give me some summary statement. Usually I do the 3 dots here for therefore. The chemical that resulted in this, therefore my oxalic acid is limiting. This is the one that ran out first. That's part A. And we end up forming 0.222 moles of the Li2C2O4 salt ends up getting produced. We never actually make it up to the 0.270. Now, naturally, the question comes to, well, how much excess remains? So sure, the oxalic acid is cut out based on the amounts that I gave you. If you went to buy more oxalic acid, the situation may be different. What I'm going to do now is I'm going to try to figure out, well, how much of the LiOH is left over? When it says how much excess remains, usually you put it back in the units that I give you. So if oxalic acid was excess, I would figure out how many grams of the 20 grams left over. This time I have 600 milliliters. How many milliliters of the lithium hydroxide is left over? So let me just draw you a quick picture of this one here. I started off with 20 grams. This was our oxalic acid, H2C2O4. This one, based on my calculations, should produce 0.222 moles of your lithium oxalate salt. Of the other chemical here, I happen to have more of it, although it's a little bit hard to show on pictures. 600 milliliters, this is 0.900 molar. That was the solution. This one could have actually created, of the same chemical, actually a little bit more. So 0.270 in total. We know how much really got formed was only the 0.222, right? The extra amount actually didn't get formed. By that point here, the 20 grams has completely got used up. At this point, there's 2 ways of doing it. Both ways require a calculation as well as a subtraction. Because we now know this chemical is currently limiting, this 20 grams becomes a really useful number for us. Unlike the 600 where some of it reacts, some of it doesn't, what we're going to do is we're going to calculate. So method number 1, you only need 1 of these methods. Method number 1, find out the volume of the second chemical, which was our LiOH, consumed, and subtract. Right, so I'm going to calculate over how many milliliters of lithium hydroxide. So jump from the oxalic acid just over to the lithium hydroxide, starting with the 20 grams. I actually had a lot of the numbers from earlier already. 20 grams of your oxalic acid, H2C2O4. My molar mass, I believe, was 90 grams per mole. My mole ratio was for every 1 part oxalic acid, there was 2 parts lithium hydroxide. And then for the concentration of lithium hydroxide, 0.900 moles for every given 1 liter. 20 times 2 divided 90 divided by 0.9. By the time the 20 grams actually got used up, we actually ended up using up 0.493 liters of lithium hydroxide. So out of the 600 that I started with, 600, this is milliliters, I minus off this is 493 milliliters. As expected, I still have a little bit left, so what is that? 107 milliliters remain. You could otherwise also factor in, well, it actually is 600 milliliters. You can figure out, well, what concentration do I have left over in 600? But that's just one way of showing it. I'm going to show you the other method of doing this as well. For method number 2, also requires a subtraction. Based on the picture, let's figure out how much extra product I could have made. So, find out the extra Li2C2O4 could have formed. How much could have been made? and then do the calculation afterwards. Naturally, I find people like doing this way because the subtraction is a lot easier, right? What if I took 0.270 and I minus off 0.222? Well, I could have gotten, give or take a little bit of rounding here, I could have gotten an extra 0.048, but my production stopped. You have to be careful. This one here is still Li2C2O4. This is not the excess. This is just the amount that could have formed, but definitely, even by the time the limiting was eating away at this lithium hydroxide, I still have enough lithium hydroxide to end up forming up that difference, forming up that amount that never got made. So you still have to do a calculation. It's not easier in that sense there. How many milliliters of lithium hydroxide would I need if you intend to make an extra 0.048? It never actually gets made because I actually ran out of the oxalic acid. Again, I have a lot of the numbers from earlier here. My mole ratio, I believe, was 1 mole of Li2C2O4 is 2 moles of LiOH. And then for concentration, for every 0.900 moles, this was a concentration. This gives you a liter. And this one should give us our excess again. 0.048 times 2 divided by 0.9. This gives me, give or take, 0.107. And that's liters. And that agrees nicely with 107 milliliters. So make sure you know at least one of these methods to do the excess. You don't need to do both. I'm going to finish off with one last step here. All of these ones here have been pretending a perfect world. So if 20 grams completely gets used up, I should get this. All of our calculations have been what's called a theoretical yield. We've done multiple labs by now here, and there's always going to be problems. Random errors, systematic errors. Maybe the chemicals we're dealing with aren't quite pure. Maybe the reactions don't quite go 100%. A whole host of these problems here makes it that our actual yield is usually going to be less than these numbers. It's not small number divided by big number because, in fact, both of these ones here are actually theoretical yield. Both of these are in a perfect world, theoretical yield. In the actual yield here, we're going to get even less. We already were expecting 0.222, not quite the 0.270 because the one ingredient ran out. But in the real world, we'll probably get even less than the 0.222. So let me just write this down for you here. Usually, the actual yield is even less than in my numbers here with the 0.222. This number here couldn't be calculated. They would have to give this to you. So what they can ask you is they can calculate the percent yield if one time I did the experiment, maybe I only got 0.180 moles. Right. So we would have to be given this number here. And all I would do is I'd say, well, based on the one that ran out first, I should have produced 0.222. If I do that ratio there and I calculate over a percent, 0.18 divided by 0.222, this one gives me an 81.1% yield. And it's just one small little twist at the end. My actual yield is even less. It doesn't mean your chemistry is bad. Some reactions just don't go forwards. Maybe there's a whole host of different problems. You try to tweak some conditions here. Let's say we then manage to improve our yield the second time around. Let's say we improve it to 92% yield. In that case there, I can ask you for the actual. And essentially it just amounts to, all right, so if I was supposed to get 0.222 moles, and now after you tweak the conditions, you manage to get 92% of what we did. We're doing math with percent, so I put that as a decimal. 0.92 times 0.222, I end up getting an actual yield 0.204 moles. So just one small little twist of it. That's the percentage yield. Keep practicing through your problems on the review sheet, and then we'll go from there. Thanks, guys.